So we'll see what resemblance the title of this talk has to what eventually comes out. But before that, just a little bit about me. This is my life in programming. Won't go over the whole thing. Emphasis on Python for a while, C++ for a while, though these days C++ is about 10% of my work, I'd say. A deep love for Erlang OTP, and an abiding interest in language design, type systems, type system design, etc. So oddly, despite all that, I'm a lawyer. I'm a practicing litigator. I work at Phillips and Cohen, which is dedicated 100% to representing whistleblowers under various statutes. So in the United States, whistleblowers can bring cases or file reports, and under various programs, they get not just protections, but a percent of the proceeds if the case is ultimately successful. It's a full contingency practice. It is not the subject of this talk. But just because it's odd enough, I'll talk really briefly about the sort of stuff I do and why I spend most of my time as a lawyer programming. So my caseload is a combination of cases about a variety of technical subjects and cases that are not necessarily about technical subjects, but that have up to terabytes typically of data that we've pulled out of various companies. A lot of data in healthcare, et cetera. It's not uncommon for the technical subjects to overlap with the data-centric cases. Sometimes they come along with data that needs to be analyzed. And then there's this little bit, and Python is great for this too, where you can just think of wrangling. There's evidence in the case, but it's evidence that needs to be transformed into one form or the other. And this is the kind of thing that historically lawyers just didn't even look at directly, and we've brought that capability in-house. So that's been very interesting. It does bring me to an important disclaimer, which is that the law firm of Phillips and Cohen LLP does not necessarily share my views of Python's optional static typing system. So what are my views of that system? In short, I think it's great. I think it's settled down. I think it's pretty rich and pretty expressive. Obviously, it's still under some development. And this talk is going to be somewhere between the dimensions of an introduction to that system, a discussion of managing complexity in application development with the odd use case of desktop apps that we end up doing a surprising number of for various kind of domain-specific things at my job. And maybe, if we have time, a bit of a philosophical discussion about what you want a type system to do. What's it there for? Because that's an important design question that maybe sometimes gets assumed away at the beginning of a conversation around types. So this is going to leave us with a collective choice. This talk is a bit overstuffed, and I can lean more in the direction of the typing, I can lean more in the direction of the GUI stuff, or I can try to strike a balance. But just before we get going, a show of hands, how many people are using optional static typing in their programs pretty strictly, pretty regularly? Okay, little less than I'd expected actually, so maybe I'll lean more on the typing. Maybe 10, 15%. How many people would consider themselves really proficient users of the type system? I wouldn't necessarily consider myself in that category. Okay, a few, and I may defer to you. Different things come up. And does anybody do desktop programming? Okay, good, so at least a few. So sound all right if I lean more on the intro type stuff, since that's not everybody's bread and butter? Seeing some thumbs ups, okay. So benefits of static typing. 3 categories typically get cited. On the one hand, type safety. You are able to, in a statically typed system, catch errors that would otherwise be runtime errors. This does not mean you don't have to write tests. In fact, most of your tests, if you're writing good tests, as I'm sure all of us do all the time, are going to be not dumbly checking everything for a type conflict. So you're not even necessarily going to write that many fewer tests. However, a lot of the silly stuff will get picked up right away, and the failure will be very early. It will be when you write the line of code, rather than a long time later after you've tested it or hit it in runtime. Excuse me. There are also performance considerations. This is just starting to come online in Python. MyPyC is interesting. There's now the optional jitter that's slowly being worked into the language. But I'm not really going to focus on that. I think my interest in static typing right now, as a largely solo developer, really is about what it can bring to the coding experience, which I found pretty remarkable. And in contexts where I didn't actually think it would be worth the trouble, it's ended up leading me towards really, I think, better code. and a clear understanding of what's going on. So let's get one thing out of the way. You sometimes hear about weak types, and this needs to be strengthened by a type system. In computer science, these aren't very precisely defined terms. And I won't pick through this too slowly, I hope, but just as a bit of a group exercise, what happens if you add 2 plus the string 3? Right, type error. Python 2, same behavior. JavaScript, 2, 3. Yep, famous example. My beloved Erlang appropriately throws an exception. And back in the realm of sanity, C++, ultra strong typing system, you're fighting it all the time, it won't let you do anything. So that presumably throws a 3-character string REE. And the security talk earlier, a lot of that ultimately comes from this. I'm cheating, of course. It's C++, you're supposed to know to do something else. So instead you use standard string, and then you get the expected warning from the compiler. Just a couple more of these. Okay, show me a language where this is true. I'd be very interested. So obviously here you get a warning right away in C++ with this confusing note about the ISO standard, and you ultimately get the same thing. And one last example, 2 less than the string 3. Python 3, type error. Python 2, anybody remember? Python 2 had a total ordering. So this was a subtle but pretty big change that got dropped off in 2 to 3. So it's arbitrary which is greater and which is lesser, but you can do comparisons between the sort of basic stack of value types. JavaScript finds it as false. Erlang finds it as true. It also has a total ordering. And 3 is an atom, not a string, so it gets complicated. And in C++, you get the same thing. We could go on in this vein, but just one quick note. Oddities often show up too in type conflicts around falsiness. So it makes sense why this is true, but it's a little strange if you look at it, right? In any case, I don't think the static typing really has much to do with this strengthening, which that has to do with what happens when types collide, whether they cooperate or whether they have a fight with each other. I think that static typing really has to do with exactly that. What you can be sure stays in place as your code is operating. So there are a few different shades of the word static here. You can think of static as static analysis. So that's any analysis done without execution. So let's do a little bit of static analysis right now. Here's our 2 plus 3. And I'm going to prove that this little program is not executing because I'm going to insert an arithmetic error beforehand. Now, static analysis is not necessarily hard. In fact, Python's batteries include a tool that does a lot of the hard work for you. So if you take the abstract syntax tree and you fire that code at it as a string, you'll get this. And this would be, you can imagine, you have to think of a lot of individual examples, but you could crawl this data structure, you could look for divs that have a 0 on the right, you could look for adds that have a type conflict on the left and right. And in, a day, you could write a reasonably capable static analyzer that would catch a lot of these very, very basic conflicts between types. That would be like a end of first semester Python programming project. You wouldn't get a lot, but you would learn a lot and you would get some useful results. And Python even lets you bring that into the IDE because it's outputting where in the code each of those errors take place. So you can see how you would begin to work the problem, right? So, of course, it gets massively more complicated when you consider that Python has very dynamic assignment. So you've got static typing, which is types available without execution. And you've got static type assignment, a language in which variables can only store one type. So let's look at this quickly. Python, there's our error. But if we look at the syntax tree, now we're not getting any help in terms of identifying. We can no longer just look at the operation and look at the left and right-hand side. We have to start building a model in our hypothesized type checker that actually goes through and starts doing what the Python is doing and associating each of these variables with a type. So you can imagine how complicated this gets and how quickly it gets complicated. Let's compare C++. So in C++, right away, you get an error here. There's no match for the operator. C++11 has type deduction, so you don't have to do it. Actually, I'm kidding. This will give you re again, so you have to go through some extra steps. However, what you're getting from C++ is right at the level of the language's syntax and semantics, information that you can rely upon in order to reach these kind of conclusions. In Python, it's dicts all the way down, and anybody who doubts that can run this code in an interpreter. Is this people know about globals? In Python, assigning to a variable is essentially syntactic sugar for putting a value in a dictionary. It's sort of different at the symtable level, but symtables also use dictionaries, so it washes out. Why don't we talk a little bit then about Python's optional static typing ecosystem? So it begins in 2006 with this idea that it would be useful for all sorts of reasons to be able to store things in an annotations variable under a function. You could put anything you want in there. Type hinting was obviously mentioned. There were lots of other things that were mentioned. In 2014, based on 2 years or so of work done by MyPy, the type hints case starts leading, and that's followed quickly by a discussion of type hint theory and a brief overview of some other languages. Doesn't mention Erlang, which actually had optional static typing right since the beginning, but that's a story for another day. Very helpfully, there's a comparison of type checkers. And I think what you see here is that right now, the Microsoft's type checker, which is the default for VS Code, seems to have pulled pretty far ahead even of MyPy. Time permitting, we'll discuss some behavioral differences at the end. But it's pretty impressive. And on the other hand, I don't know what's going on at Google, but PyType really seems to have fallen off. I guess it has a lot of internal use, but on the benchmarks, it's just not performing right now. Here's a quick overview of the PEPs. You can go look at them. I would love nothing more than to pick through them in detail, but we surely don't have time. And anyone who wants to know the current state of the system, typing.python.org is the reference. So let's look at fully dynamic Python, defining the successor function. This is going to be a runtime error. And let's look at how optional static type hints, and I'm sure most of people have seen these even if you haven't used them, it can stop your build, but it can also empower the IDE to tell you as soon as you type it that down the road you're going to run into a problem. So we're going to take a hard turn and talk about GUIs for 10 minutes. Anybody here done PySide or PyQt programming? Okay, just a few. So I'm going to try to give you the flavor of what this is like in Python, an incredibly dynamic, incredibly fluid language, and leave you with a taste of how I think the type system can actually help support that dynamic behavior rather than being something that you have to fight. So this is as short as it gets in PySide. PyQt is basically the same with some licensing differences. If you want to play nice with the system, you do this. If you want a minimal visible example, you have to create a window and show it. Not super impressive. You can quickly call the window manager, then you can do some basic stuff. So pretty efficient, pretty mature system, not a lot of code to get a result. And that's been my experience with PyQt and PySide generally. We can get widgets and windows, we can add our first type annotation, we haven't needed to do it until now, and we can get hello world. I'm immediately bored with hello world. So let me see if I can get this over on the monitor. We're going to do world hello. Okay, so this is hello world in every language supported by Google Translate. And this is now up to about the logging, which I'll talk about in a second, adds a couple of hundred lines, most of that styling, but this is now up around 100 lines of code. We can look at it quickly. Is that visible? Yeah, good. So we've got hover over, we've got a button, we've got a cycle option, and we've got, we can go down here. Now it's cycling quickly. Now it's cycling really quickly, etc. I might run that again in a second. But if people are interested, I'll just run through and show you what this looks like. Bunch of imports. This is the data structure for the hellos. The idea is just to get a flavor of this. And you've got sensible default behaviors. Whoops, you got sensible default behaviors so that you can get a lot of things connected right off the bat. So the originating experience of this talk for me was having a much more elaborate project that I was trying to refactor and sort of continue development of. That was a GUI. I've extracted little bits for this example. And in the context, I thought, well, let me try to finally be disciplined about using the type system. I thought it would be a dreadful experience. I decided to stick it on strict. I'm sure I'll dial it down. And it actually led me in some surprising directions. For example, that logging function, which I'll release after this talk, put it up on GitHub somewhere once I've bulletproofed it. That's a very useful thing to have in a GUI because you've got a lot of different things happening at once, right? Complex interactions, and it's just helpful to have that kind of automated output. So is that a problem for the type system? No, it's not. You can do everybody's favorite decorator example, which is a function that prints its own name when it's called, and you can quickly pipe it into the Qt logger with no trouble. Now, if people used, probably most people have used decorators. How many people have written a decorator? So decorator is just a function that returns a function, sloops it in place, and we get sweet, sweet syntactic sugar that saves us from having to do some pretty ugly, pretty repetitive code. So what we have here is a type system example. And I would say this is getting about as far out as I had to get with the type system to get it fully strict compliance under PyWrite. So I think it's a fairly realistic example. And the key is this log func inner component. So what you've got there is essentially a callable with an unlimited number of arguments of any type. That ... is variadic. And takes a function and it returns that function. So this was a lot worse a few versions of Python ago. This is the kind of thing that's been getting better as the edges of the type system have been improved. It's about to get a good bit better, I think, in 3.14 for reasons which I won't go into. But this decorator is nice. I won't go back to the example for reasons of time, but what you can do is drop this on any function in your program, and it will automatically pipe through and ping your log if you have the logging level appropriately set and the log is turned on, and fully type compliant. You don't have to disable anything, it just works. A wilder example, I have a choice about how to proceed here. We have a few more minutes. Let me work through the theory and then I'll try to motivate the example, which is the sort of far reaches of what I'd hoped to talk about here. So this is an interesting case, I think. PyLance is able to do this. X returns 3, Y returns X plus 3, Z returns X plus Y. It's able, first of all, to understand that not all cases are going to be caught by this match statement. And it's also able to understand that this case, case 10, is never going to be reached. And the reason it's able to do that is that, you'll notice I haven't put a type signature here. It's inferring not int, but the literal type. And in particular, only the literal type corresponding to the integer 3. And it's able to carry that through. Now you can easily break this. This isn't something that you can count on. But if it's working in a stable domain, it can actually be pretty wonderful when you're dealing with it in the IDE. So what happens though, is that if you do explicit specification, now I say int, it's still getting that it's not exhaustively handling all values because I don't have a fall through at the end of the match case. However, the magic is gone, right? It can no longer track what's actually happening to the number 3 as it's going through these basic arithmetic operations. Instead, you end up in the system where you're by being more general about your intention, you're losing the ability for the IDE to actually direct you in a way that wouldn't be useful if you're building a library, but might very well be useful if you're building a program. For example, a GUI. So this is where people may leave the room, but you may decide in the course of your quickly banging a GUI together that what you need to do is give users the experience of tight coupling between all of these components, but you don't want to write tightly coupled code. And so you have to do a lot of passing of information and messages back and forth. Good GUIs depend heavily on context, the state of the system, what the user's trying to do, avoiding surprise, making operations more efficient. So you might decide, if you're me, that you want to pass, generally speaking, an enum, and this is an old C standard. This is still how SQLite is written. And there were reasons for that back in the day, but with match case, it's actually, I think, going under a little bit of a renaissance. An enum that defines a set of errors, and then those enums can either carry information with them, or they could just say, this was successful. So those can be errors or warnings. They can be successes that carry information. They can be successes that don't carry information. And it turns out that this kind of logic, where the type system is able under certain circumstances to identify cases that you have and haven't met, essentially gives you something like, it's not checked exceptions, it's more like checked return codes, where it will tell you if there's a case that you're not accounting for. It will actually complain. It can identify all of the different code paths to the returns, assuming you're within its capability, figure out the set of all of the literal enums, and tell you right away if you change something, if you add something, you need to go over here, here, and here, and accommodate that. Again, not for library development. Very, very handy as you're trying to manage this ballooning complexity of what goes on in GUI programming. So I like that. And another thing I like is this. This is the outer limit. We have just a couple moments left. What you can do with the type system is essentially inject an additional code. So imagine that I have some set of methods, and all of those methods I want to fail gracefully if I'm not connected to a database. Common situation in a GUI. You haven't opened something up yet. And of course, I want to disable the user interactions that are going to lead me down that path, but maybe I'm going to forget to do that, right? What I could do instead is another decorator that takes everything the function was going to do and says, I'm either going to return whatever it was going to return, or I'm going to return a not connected error. This is type safe, and this will work if the stars align with that IDE behavior and give you essentially what you want, which is meaningful real-time reporting as you're building your program out about what's happening. Now, there's a big caveat. This does not work with MyPy. I went down a whole rabbit hole around this. There's an extensive discussion. The Python typing spec actually requires that if you don't specify a return type, that type is inferred to be any. But Pywrite and Pylance simply don't do that. They're willing to go ahead and do this. It's like auto in C++, actually. They're willing to go ahead and do this when it's a benefit. Probably that has to do with the fact that it's more IDE focused, and MyPy is taking a more conservative tack. However, when it's working, it's frankly magical, and it's really helped me. So I think what I'm arguing for is dynamic static typing. I think that there's a way of using the Python type system to fluidly develop your program, and it doesn't require backing away from it or being particularly gradual about it. So I encourage everybody, whatever your domain is, turn it up to strict and see what happens.